Hey, what's up everyone? It's Dr. Lanier here, coming to you live from, well, my backyard. If you know one thing about me, you know that I love fire. I love to blow things up. But what I love the most is the chemistry behind the fire, the molecules in motion. And I guess that's why they call me the chemistry cat, am I right? So if you're ready to do some chemistry, let me grab my blowtorch and let's get lit. So when you hear the word combustion, what do you think about? Probably a big boom and lots of fire, right? That's what I think about. And so today we're going to take a look at the most general form of combustion. And we're going to look at combustion that results in a fire or a flame. Because not all combustion reactions produce a fire. But where's the fun in that? So, in order to have a fire, you need three key ingredients. The first, you need a fuel source, and we're going to talk more about this one because you have a ton of options here. The second is you need oxygen. You can't have fire without oxygen, so this one is critical. And lastly, you need an energy source or a spark or something to catalyze the reaction. But before I go any further, I want to take a step back and I want to explain what all of these letters and numbers really mean. And so in chemistry, what we do is we write chemical equations just to represent a chemical reaction that's taking place. And you can think about it as a before and an after. You can also think about it as a mini recipe. And so on the left side of the arrow, you have what's called the reactants, or these would be your ingredients. And so if we were baking a cake, these would be your eggs and your sugar and your butter. And on the right side of the arrow, these are your products, or what you make in the chemical reaction. Or in this example, your cake that you bake. So a good sign that you're dealing with a combustion reaction includes the presence of oxygen as a reactant and carbon dioxide, water, and heat as products. Now, inorganic combustion reactions might not always form all of those products, but they're still recognizable by the reaction of oxygen. And so now let's take a deeper look at this reactant, the fuel source. So one of the most important applications of chemistry is the study of fuel. And fuel basically means a chemical that provides energy. And we use fuel in nearly everything that we do. So food provides fuel for our bodies, gasoline provides fuel for our cars, and many different chemicals from coal and gas to uranium provides fuel to the power plants that generate electric power. And when we use fuel, that fuel becomes a reactant in a chemical reaction. And so now I'm going to walk you through three different types of fuel. So we have solid sources of fuel, liquid sources of fuel, and gas sources of fuel. So we're going to explore liquid and gas sources of fuel in future videos. But today we're going to take a look at my favorite solid source of fuel, cornstarch. Yep, cornstarch. So we're pretty familiar with coal and wood as being great sources of fuel. We've probably all been around a campfire where we burned wood to roast marshmallows and cuddle around the heat. But turns out that wood and cornstarch are both carbohydrates. So cornstarch should burn, right? Well, let's find out. So cornstarch is supposed to be flammable, right? Let's see if we can light some on fire. Why didn't it burn? Well, it did burn, so that brown residue that you saw on the top of the cornstarch was a result of it burning. But what about the fire and the big boom? Well, if you think back to our three key ingredients. So number one, you need fuel. Okay, cornstarch, got it. The second is you need energy or heat to ignite the reaction. Blowtorch, present. But the third and the most important is oxygen. And so yes, there's oxygen in the air all around us, but But if you think about the pile of the cornstarch, only that outermost layer or the top was exposed to oxygen. And so in chemical reactions like this, surface area is key. And so you can think about it like you do in your everyday life. So when you're making a cup of coffee, for example, sure, you can throw in some sugar cubes, but that's going to take a lot longer than if you put in, say, a scoop of sugar. And the reason for that is the surface area of the scoop of sugar is a lot greater when you break up that sugar. Another example is if you've ever tried to light a fire with, say, like a wood log, that probably took you a really, really long time. Actually, it probably didn't work, which is why we cut up the wood to smaller pieces to expose more surface area. And the last way that you can think about it is like in a Rubik's Cube. And so if you have a Rubik's Cube and let's say each square, each surface of each little cube is 1 inch squared, then the entire surface area for that cube is going to be 54 inches squared. But what if we broke up the cube into all of the little cube components? Well, now you're going to have a surface area that's much greater. Actually, you're going to have a surface area of 162 inches squared, a lot higher. And so what if we took this principle and applied it to, say, my cornstarch? So how would we do that? I do have a leaf blower. I could use that. Don't really want to. I am feeling a little hungry. I have an idea. Let's see what I come up with. All right, yes, that was awesome. That's what I call chemistry. Now remember, don't try this at home. And dads, that goes for you too. But if you enjoyed today's video and you learned a little chemistry in the process, I hope you tune in next time as we explore liquid sources of fuel and gas sources of fuel. Until then, see you later and stay lit.